We can also derive a formula for the area between a curve and, say, the lines theta equals A and theta equals B in polar coordinates. And we do this with a Riemann sum. So remember that the area of a segment of a circle of radius r, where the angle at the origin is theta, is given by r squared times theta over 2. So to estimate the area trapped between this curve r equals f of theta and the lines theta equals A and theta equals B, I can slice this interval of angles from A to B into n subintervals, and theta naught is A, theta 1 is A plus B minus A over n, and theta 2 is A plus 2 times B minus A over n, etc., etc., just as I would for a regular Riemann sum. The portion of the region here between the angles theta I minus 1 and theta I looks a bit like a slice of a disk, and the angle at the origin here is delta theta, or B minus A over n. The radius of this slice of a disk is roughly f of theta star for some specific theta star in that interval from theta I minus 1 to theta I. So the area of this slice is f of theta I star squared times delta theta over 2. And when I sum the area of all the slices, I get this Riemann sum, the sum from 1 to n of f of theta I star squared over 2 times delta theta, where theta I star is some angle in the interval from theta I minus 1 to theta I. And of course, if I take the limit as n goes to infinity of that sum, then from my work in Calculus 1, I know that that limit is the integral from A to B of f of theta squared over 2 d theta. And of course, f of theta is r here, so this is the integral from A to B of r squared over 2 d theta. And this is exactly the area trapped between this curve r equals f of theta and the lines theta equals A and theta equals B. Well, let's apply our formula. Suppose I want to compute the area bounded by the curve r equals sine 2 theta for 0 less than or equal to theta, which is less than or equal to pi over 2. The graph of this equation is this 4-petaled flower. As theta swings around from 0 to pi over 2, we get one of these petals. So using our formula, we have the area of that petal is the integral from 0 to pi over 2 of sine 2 theta squared over 2 d theta. Of course, here f of theta is sine 2 theta. And we can use the half-angle formula for sine squared 2 theta. So sine squared 2 theta is 1/2 into 1 minus cosine 2 times 2 theta, which is cosine 4 theta. And we get the area as 1/4 the integral from 0 to pi over 2 of 1 minus cosine 4 theta d theta. And this is 1/4 theta minus sine 4 theta over 4, evaluated between 0 and pi over 2. And our final result is that the area of this petal is pi over 8.